I'm so happy to introduce her. She actually grew up in Alfred and took her first college course, I think, from me. She took my FYE class. And then we lost her, but it wasn't too bad because we lost her to Middlebury, where she studied with a friend of mine. So she went to Middlebury College, got her bachelor's degree there, then got a PhD from Cambridge in England, and has done lots of work on climate change and spent some time in Alaska, where she actually met with and maybe worked a little bit with David Tomeo, who was another alumni from Alfred University. So, and this semester she invited another alumni, Ben Pelto from Alfred, to speak to her class. So there's lots of connections there. But I'm going to turn it over to her, and she can tell us about some of the work that she's been doing. I should say she's now at Colby College, where she's an assistant professor of geology.
Yeah, visiting, just here. But thanks so much, Michelle. Yeah, no, there are all these connections and they always seem to lead right back to you. So yeah, it's amazing. I don't know, throughout my career so far, everyone somehow has crossed paths with you at some point or another, which is kind of cool. So I'm going to share my screen here and get started. All right, and so can everyone see the title slide here?
Yes.
Awesome, okay, perfect. So yeah, I wanted to talk today to you guys about Denali Park and tracking snow depth, which was a project that I actually did last winter. And I was pretty excited to talk to you about this topic, partly because last year you had a seminar talk from David Tomeo, who is now managing the kennels, so the sled dogs that are up in the park. And so it all starts with Alfred, right? This picture is of me, I think when I was about 5 or 6. That's where I got the skills I needed in order to start this project, at least from a physical standpoint, right? So thanks to all of the snowfall and skiing opportunities that I had in Alfred, I actually, it was one of the requirements for the job, was to be able to actually ski for long distances. And so that was one of the reasons why I ended up there, which is pretty cool. All right, so today I have a couple of topics that I wanted to cover. One is just to give you a little bit more of an overview of Denali Park, because it is such a beautiful place and a great place to visit. Some of the research that's going on here, it's pretty diverse. And then the project that I worked on, which we like to call the Forgotten Season project. And so a couple things about that, and then just wrap up. So Denali Park is this beautiful, humongous park featuring the highest mountain in North America. So Denali, known as the Great One, used to be called McKinley. And this park is 6 million acres in size. And I always like to give context for that. So 3rd largest national park and the same size as the entire state of Vermont. So that is the playground, right? Huge park. And it is located at 63 degrees north, which is basically covering this entire subarctic zone here, is more or less that latitude range. And so it has a lot of the same features that you would find in an Arctic environment. And actually, in a way, it's a good predictor for what will happen in the Arctic in the future. And Denali itself is located pretty far into the interior of Alaska, and that makes a big difference, because if you're on the coast, you see a lot of heavy snowfall, a lot of rain, some warmer temperatures, but the interior of Alaska, where Denali is relatively dry and has this quite cold interior climate. And in some years, I think may have less snowfall than a place like Alfred, actually, and very commonly would have less snowfall, actually. All right, so a few things that the park is known for researching. One of the things that I really wanted to get out of my experience working here was to understand how the national park system actually functions. And each of these parks has something called a resource division. And in that resource division are various types of physical scientists. And even for a park that is as large as Denali, you may just have like one geologist or one biologist, one geographic information systems person. So these jobs are very coveted, very hard to get, and I would love to get my hands on one of them. But they do fantastic research, and it's very collaborative. So the thing that really impressed me about it was that it's like, you know, you have colleagues that are seeing each other every single day, collaborating on getting field work done throughout different times of the year, you know, changing focus on what needs to happen. So it's a very collaborative, dynamic environment, especially in Denali. I guess I was also lucky because Denali just has a really great resources division. But they're looking at trends in large mammal populations. You might see, you know, studies about caribou or about these Dall sheep, or, you know, about large sort of wolf packs that they're tracking throughout the park. There's a lot of work on golden eagles and songbirds migrating through the park system. And what's really special just is also that they have this entire massive area that is preserved, that is not touched by humans for the most part. And that, you know, as employed government researchers, you have full permission pretty much to use and for your research. And on top of that, really the ability to do long-term studies, which is something that I think academics in universities often don't have the chance to do because grants are pretty short. So if you have the chance to do sort of a long-term study, you're living in this place, you know, you're like on the ground all the time, really observing all the changes going on. It's kind of a unique way to do science. So from a geology side of things, people are really interested in permafrost thaw throughout the park. There is permafrost almost throughout the entire park, varying sort of grades of continuous or discontinuous permafrost. Many shallow lakes because of that permafrost as well. It's such a dynamic environment. So all these little shallow lakes that have been recently created. You have people monitoring, for example, also the glacier activity. So we have the Alaskan range here. And then this past summer actually was a really big story. It was even featured in the New York Times. This glacier that you see down here in the bottom right-hand corner, the Muldrow Glacier, started to surge. And it basically, when a glacier surges, it moves like 50 to 100 times faster than it normally does. And this is something very peculiar. Not every glacier does this. Only a small percentage of glaciers will actually surge. But it was having a cycle, like every couple decades, the Muldrow Glacier surges. And essentially it's, you know, we spent a lot of time actually working on this in the park as I was leaving. And we were looking at how the bottom of the glacier gets lubricated by all of this water that had accumulated. And then it sort of helps that glacier just sort of slide along really quickly. And then that water is gone. And so it slows down again. And then it takes a while, like decades, for that pressure to build up for the glacier to start surging. But pretty interesting story. So lots of active things. The other thing I wanted to highlight was this is the park road. So there is one road that snakes through the park, really gets into the center, and that's how visitors experience the park. And the park was actually closed early this year at the end of the summer because they have a landslide. This landslide here, you can kind of see where the road drops off. And they had to close it because it's moving several inches per day. It's just sliding. And that's one of the active hazards in the park, one of the problems they're dealing with, and very expensive to try and fix in some ways. Yeah, but it's the lifeline of the park because they generate all of their revenue from visitors who use that road to get through the park on buses. And if they don't have that lifeline, then the park doesn't have its funding. And also a lot of the other parks in Alaska actually depend on Denali for money because, you know, that pot of money gets shared amongst all the Alaskan parks. So it's pretty important. And there's also really interesting research going on with listening to changing soundscapes. So this is a picture of David Betchkel, who works actually on just putting up monitoring equipment throughout the park to listen to how sounds of the park are changing, how human activity is actually changing the normal natural sounds. He actually went to that surging glacier this summer and took some recordings of just the cracking and booming of that glacier moving really quickly. And so that was part of that study. And something else that of course also happens is a lot of air quality monitoring. So it's a very pristine park and they're able to track aerosol contaminants that come from very far away. So lots of exciting collaborative research. And then the part of the project that I'll talk to you about more today is actually the part that intersects between snowpack and vegetation. And you might not really think that those two things should go together at first, but by the end of the talk, hopefully I'll convince you that those two things are actually pretty related and sort of have feedbacks that go in both directions between the two. So I'll sort of get a little bit more into that project now. So I was working with Sarah Sten. She's the park's botanist. And I was there for the winter season 2020 to 2021. And there have been sort of other guest scientists working with her previously and also this winter to sort of continue doing this long-term snow depth monitoring throughout the park. And I should also say that this is an opportunity that undergrads and graduate students, really anyone from the age of 18 to 30 can apply for. So this is the Scientists in Parks program, and the applications for summer jobs open in early December. So you can go to that website that I have linked up there in the upper right. Whoop, sorry. I think I have a automatic slide continuation, which is I forgot to turn that off. So you can go apply for one of these positions. There's positions all over the US in different parks, and it's a great experience. So I was on the tail end of my eligibility to actually be able to do one of these positions, and it was really worth it. Really fun experience. All right, and one of the reasons that made it such a fun experience, I should say, is that we got the help of these amazing sled dogs. So they were the reason that we were able to get into some of the deepest parts of the park where you're not allowed to have snowmobiles, no kind of motorized equipment. And so these sled dogs here are kept with the park and cared for and trained. And they're basically considered to be park rangers, canine rangers. And they do a lot of the work in helping to sort of get you out into the field and carry equipment. And Denali is pretty special in that respect because it's the only park that has these sled dogs. And one of the reasons they do this is partly to preserve this traditional Alaskan way of moving through the landscape and transporting, and also to preserve the breed of dogs. So this is kind of a special thing they do. They actually try and actually preserve one specific quite large, fluffy, cold resistant type of husky to do this work in the park. And one of the sort of intersections with the project that I was doing, besides just hauling equipment, is that they actually do the weather station readings every single morning because they have to be there to feed the dogs. So in the morning, they're also going to go and check what's the snow depth, what's the temperature, and they'll record that every single morning. So it's a pretty cool way to have a long climate record at the park headquarters, and a nice collaboration, I guess, work that they do with climate scientists. This is a picture of one of the mushers, one of the people who works with the sled dogs, Mitch. He was doing a reading that morning, so I took a picture for this presentation. And basically that station has existed in some form or another since 1927. And has moved around a little bit, but essentially exists in its current form in some way. And that station was one of the data sets that I worked with. So it's one of the longest records of snow depth in Alaska, gets used by a lot of research groups, and just like a very well-kept, well-maintained record that everyone can use. And so the time that I actually spent in Denali, I wanted to share a little bit about the different seasons that you might expect to see. So compared to Alfred, well, I guess in Alfred, you could almost say that it's like in Alaska. Your summer and fall lasts about 5 months. So it's May through September. So these are really short summers. And then you get into the winter time, and that's really the majority of the time. So it's a lot darker, about 7 months of winter, October through April. And I should also highlight that this beautiful illustration here was made by Tracy Faber, who was a scientist in parks intern as well some years ago in Denali. And so she made this depiction for Denali specifically. So you can see the mountain at the bottom and many of the animals that you would see in the park throughout the year. And so the time I spent here was pretty much from the beginning of December all the way through May. So I saw Denali in the height of winter for about half a year. And I would actually say that this is one of the coolest times to go to the park and to experience it, because it is a really unique out of world experience. And you get some of this in Alfred as well, for sure, with the snow and the cold, but there's just like an extra added level of, the change in light and the sort of remoteness that you feel, and the presence of all these incredible animals around you. And I'll show some more pictures of that landscape, but I just wanted to say that it's a great time to go visit the park, even though you might just want to go see it when it's warm out. So the time I spent there, 2020 to 21, that particular year was relatively typical as far as a comparison with 1950 through 2021. So it was maybe a little bit warmer throughout December, January, February, 2 degrees warmer, so just minus 14 on average. The record minimum temperature of that year was minus 37, and I believe that was a night where I was actually camping out. The mean snow depth was 40 centimeters, so not incredibly deep, but substantial. And then the max snow depth sort of accumulated up to almost 80 centimeters that year, that winter last year. 208 days of snow cover, which is quite a long time. So if you're a skier, you'll like it. And if you're not, then you'll be sad. And the snow sort of consistently starts to accumulate after about mid-October. You'll get earlier snowfall in September, but it usually melts. So really like that consistent snowpack begins mid-October. And then the snow off date is also somewhere in early May. And I hope I'll be able to show you some trends throughout the time, because one winter is really just a snapshot. But if I look at the climate record from the park, I can say a lot more about what's happening to that snowpack. So at this point in the talk, I wanted to go through a couple of factors why snow actually matters for this ecosystem, sort of locally and globally even. So one of the important things about the snow, which you maybe haven't really thought about a lot, is that it actually insulates and protects vegetation. So a lot of these plants are pretty vulnerable in the winter, especially if it would rain on them and then freeze, or just the wind itself is very harsh. So the snow acts as an insulative cover. And that deep snow for large mammals, on the flip side, takes a lot of energy to move through. So there's winners and losers when you have snow. It's also, it kind of really influences what happens with the hydrology throughout the year, because about 1/3 of the annual precipitation that falls in Denali is locked into that snowpack during those 200 some days. And then it all kind of melts quite rapidly at some point in May. And so that is a cycle that the plants depend on also for that water release into that system is quite important. And then finally, the snow has an important effect sort of more broadly, globally, I would say, because it reflects solar radiation. So this is an albedo effect. Basically, albedo explains how reflective a surface is, and snow is very reflective. And so if that snow is replaced by something else, that cooling effect will no longer really be taking place. So those are some of the main factors. If you look at plants in particular, let's look again at that insolation effect, right? So snow may increase, and basically the effectiveness of that insolation effect stops after about 35 centimeters. You've just maxed out on the protection that the snow is able to offer after that. But everything below 35 centimeters, you can kind of think of as sort of a gradient of protection that the plants are going to get. So if there's only 5 centimeters of snow cover, that's not really going to protect them very much. As well on that, if you start looking at the microtopography and macrotopography, just the slope, the angle, the exposure that slope has to wind or to sun, and then the little just hollows in the landscape, the places where you have large trees that protect some other plants. So that is all part of the ecology, all part of that system that's kind of allowing certain plants to grow somewhere or not. And that vegetation then can actually feed back into the snow. So it intercepts the snow and it can pile up on one side and be redistributed by the tree canopies. So really the vegetation actually also changes how and where the snow accumulates, and if it is just blown off into some other gully somewhere, or if it actually stays on that plane on the landscape. And that's pretty important when you think about on a large scale what's happening with landscapes in Alaska, in the Arctic overall. This is just one example, but this is happening all over the Arctic, all over Alaska. There is just a really prominent expansion in shrubs. So this is a photo point monitoring example from Sable Pass in 1931, and then in 2016, the same photograph showing. And you can see that in that top image, you have that same road that's going through the landscape, but it seems to be mostly grassy kind of tundra vegetation. And then just 75 years later or so, there's been a large increase in shrubs. And that has nothing to do with humans distributing, seeds or anything, or sort of any other kind of disturbance issues. It has to do with human influence on the climate. So just the sheer increase in temperature really, and related things has caused this expansion in shrubs, which is quite prominent. So this has led to a lot more capture of snow, a lot more protection for vulnerable plants, increases in soil moisture, and overall sort of this ecological shift in the landscape. There's quite a complex feedback that's going on here. So this is an image from Sturmedal 2001, a researcher in Fairbanks who's spent a lot of time thinking about what all these feedbacks actually are. And it starts with this climate warming that I mentioned, which will increase shrub density. And then that will lead to an increase in snow depth sort of locally at the landscape there, which will then increase the insolation. So soil temperature goes up. That can actually promote more microbial activity in the soil and make more nutrients available, which then feeds back into having more shrubs. And I would argue that actually sort of thinking about the climate a little bit more and adding as a sort of second loop around is important, because so that climate warming is also, for example, going to decrease the amount of sea ice in the Arctic. And that will, depending where you are in Alaska, potentially increase or decrease just the precipitation in wintertime that's falling as snow. So depending where you are, it might be an increase or a decrease. And then that will feed back into snow depth, right? And that will feed back into meltwater. That will then influence soil temperature, which will actually lead to either a thawing or sort of preservation of permafrost. And if that permafrost, for example, thaws, you might release a lot of more greenhouse gases like the methane that's trapped in, and that will then feed back into climate warming. So if you kind of take a step back and look at it, even broader scale, you start thinking about all of the implications that all of these snow and shrub feedbacks have in a broader scale. And so I also wanted to show this little video here. I like to show this. This is basically the temperature anomalies. So how far away from the mean temperature the world is from 2016 to 2020. And it's all relative to sort of the previous time period, 1950. And I want to stop it here to look at Alaska. And you can see that this entire Arctic region really has just this red, very red prominent blob representing an extreme increase in temperature, sort of 2.3 or higher degrees Celsius in the last sort of 4 years compared to the average. And the rest of the globe is also warming, but just not to that same degree. Sorry, skipping to the next slide. So this is an effect that's known as Arctic amplification. Some of you may have read about it in the news, but basically it's this effect where the Arctic is warming so much more quickly than the rest of the globe. And this is where I would say, well, why is this happening, right? Why is this happening in the Arctic and nowhere else? And the main reason for that is really the loss of sea ice. And that loss of sea ice over the years means that you have a lot more exposed dark surface in the Arctic Ocean, which decreases that albedo that I was talking about. So your open ocean will only have the ability to reflect about 6% of solar radiation. Snow will, fresh snow will be able to reflect up to 90%. So it just changes the local heating that's going on in that particular region. And it's a very prominent effect. And that melting sea ice then also has other feedbacks onto precipitation because you're opening up a large expanse of water, which is then available to evaporate and carry moisture to different places. And it's not just as simple as, it's hotter and it's going to be wetter, because every single location around the Arctic and really further down into the mid latitudes and even tropics, there's all these teleconnections between these systems, and they're not going to be a straightforward feedback, right? So there's many loops involved, and it gets really complicated pretty quickly. There's a lot of people doing research about the Arctic. And so to bring it back now to Denali itself, this is an image, a photograph that I took on one of our field trips where we were measuring snow depth. And you can see Denali, first of all, in the background, quite beautiful sunny day of Denali in February, and some caribou that are running across the landscape here. They were actually being chased by a pack of wolves that we also saw. So a really amazing experience. But that albedo effect is not just happening with sea ice, it's actually also happening with the surface. So even this landscape here that you see with the exposed grass, that is not something that you would always see. So that grass is going to absorb a lot more insulation, and locally even that's going to change the types of plants that are able to survive here. So they're getting really nice and hot in the daytime, but then they're also exposed to really cold, sub-freezing temperatures and winds at nighttime. And you can actually see how much wind there is just based on sort of this icy glazed cover of the snow that surrounds it. So these are all effects going on at the same time globally, but then also locally. And if I look at the station data from the Denali headquarters park, and I compare actually just the two periods here from 1980 to 2000, and then from 2000 until present, more or less, you can actually see that there's been consistently warming throughout most of the year, especially late summer, fall, and early winter, as you move into the later decades. So there's definitely that warming trend. That warming trend is especially visible in winter. So that's the plot that I highlighted here. So this is actually from 1950 to 2020. And I believe that's something like a 3.5 degree Celsius warming trend compared to the rest of the globe, which has just been maybe just under a degree of warming. So quite a big difference. And then the precipitation trend is quite mixed. It's really interesting. So in the park, the summers have been getting extremely wet, and the fall and early winter in the park has been getting quite dry in comparison. So there's actually a contraction, I would say, of the rainfall season when that rainfall is coming down in general. And the summer trend is quite clear, an increase since 1950 there. And what about snow? So I was there to look at snow depth, and in Denali, actually, what you see pretty consistently is a decrease in snow depth year round, and not just a decrease in the depth, but actually a decrease in the number of days that are covered with snow. And there's a lot of factors that play into this, and it's partly what's actually falling on the ground, so how much precipitation is coming in, but it's also a question of the temperature and if it melts out in the fall, for example, if it's too warm to stick, or in the spring, if it's too warm to survive. So those snow cover days depend a lot on temperature changes as well. And so this is a figure that I made showing basically the timing of the snow season. And there's a lot of variability from year to year, but essentially you can see that there is this later onset of the first snow, so about 9 days later onset since 1980. So 40-year difference, basically showing 9 days later onset of snow, and then that last snow, how long it survives on the ground before it melts, is only about 1.8 days earlier. And I think that has to do partly with the trends that we saw in precipitation, having a drier fall, and then also having sort of warming throughout the year. There's also, interestingly, and I don't really know why this is happening, 26 days later date of maximum snow depth. So it seems that actually the snow and when it's falling and how it accumulates is also being influenced by climate in some way. And so this really implicates, has two big implications for the park. One of them is thinking about the severity of the winter, right, for the plants and so on. But then also meltwater onset. So when does water become available in spring, and how much of that water is actually there to melt out? And I had said before in the previous slide that snow depth is really variable from year to year. And I just wanted to show you how extreme that variability actually is. So this is a plot from 1950 to 2020 showing the average snow depth throughout that snow season. And it ranges really from super low. So 1992 is the really, really high record year. So there was an average snow depth of 88 centimeters and 241 snow cover days. And then just a decade later, you get to 2002 and you have this really low average of only 7 centimeters of snow depth, like you can barely ski on it, and 128 days of snow cover. So just a huge variability. And I was curious why there is that much variability from year to year. And I found out that one of the reasons for this is the Arctic oscillation, which you may have come across also in the news at some point. When you look at, for example, this negative phase of the Arctic oscillation, there's been a lot of stories about how this might actually be causing these cold snaps like the one we saw in Texas or in New York, of sort of cold Arctic air being able to infiltrate really far into the continent. And that's driven by this, potentially driven by this sort of waviness of the jet stream, and how a lack of pressure differences between sort of the equator and the Arctic, and the warming in the Arctic, is leading to this waviness of the jet stream. So that's how you might have encountered it previously. But this is just a well-established oscillation, very much related to what's going on with temperatures also in the Atlantic Ocean and the Pacific Ocean. And there's two phases of it. So you have the positive phase, the negative phase, and one of them essentially helps to melt out the ice, the sea ice, and one of them helps to preserve the ice. And you can think about many ways of how this could then lead to effects on climate and precipitation in Alaska. So I was curious to look at an index of this oscillation. And that's what I did. So we have, again, that in blue, that same snow depth, average snow depth plot from 1950 to 2020. And then below, the Arctic Oscillation Index. And that's basically on a scale of -1 to 1. I took the annual average. So it gets measured every month, but you can average that index. And then I ran a correlation function between these two time series and saw that actually at a lag of 0, so basically the Arctic oscillation of that year seems to have a weak correlation with the snow depth in the park for that same year. So about a R value of 0.3. So maybe 30% of the snow depth can be explained by the Arctic Oscillation Index in that particular snow season. So that's definitely one of the factors. And sort of now like looping back to what we're doing in the park. So they have all of these vegetation plots that they've been monitoring at various sites, over 1,000 long-term plots that have been set up and really monitored for decades, quite diverse types of landscapes to understand how the park is actually changing. And so what we did is actually went back to those exact same plots that have been surveyed for vegetation type in the summer and went to look at them in winter time. And this is where the fun field work came in. So this is a picture of me holding the Magni Probe device that we used. It's basically a tube with a little snow basket here that you let fall, and that rests on top of the snow. And then it signals back to your computer that you're carrying what that snow depth is. And there's also a little antenna here that records your latitude and longitude, so you know exactly where you are, how high the elevation is, and then how deep the snow is. And you can just ski along and hopefully not get whacked by tons of shrubs in your face and not fall into your hips with the snow depth. And you're just trying to record as much as you can of the snow depth in these various plots around the park. And in that particular winter that I was there, we gathered over 20,000 measurements from 3 different study sites that we visited, all at sort of different intervals. We were mostly very close by to this yellow point here, which is Rock Creek. So we did a lot of sampling here, and then, took these longer expeditions where we needed the sled dogs to help us out, especially in the center of the park here in Wonder Lake. And that's, we did that one time, but intensively, and camped out and got a lot of snow data from that particular part of the park. One of the reasons why you want to go to these various plots over and over again, year after year, is to see actually, how one location is changing throughout the year. And also, every year, the snowfall will kind of come from maybe slightly different wind directions. And if that's consistent throughout the park, if you're going to have a low snow year in the headquarters, but maybe you're going to have a lot of snow somewhere in the center of the park. It's a really large park. And then also really on a detailed scale to see, like, for example, these places here where there isn't a lot of snow, is that consistent throughout the year? Is that because you have vegetation surrounding some of the area? And then over time, is it because vegetation is actually growing there or changing and affecting how much snow is falling and accumulating on the ground? So it's really a long-term monitoring kind of project that has been started. And the idea is to gather this massive data set on really many aspects, on the types of plants, on the snow depth, but then also, to understand how slope and topography is changing all of that, how altitude is changing, has sort of different effects depending which altitude you're measuring at. And so it's a really multivariate study, and it will require several more years of data to become a meaningful project. But it was a really fantastic collaboration that I had in that particular season. So yeah, in conclusion, I guess I would just say Denali Park is this dream location for long-term research projects. I learned a lot about vegetation and biology. My experience has been mostly from a climate point of view, so I learned a lot about these interactions that occur with the landscape and snowfall. And then broadly, sort of how sea ice in the Arctic affects all of that and sets the stage for it. So lots more to learn, and I'd encourage all the students to apply to this program and try to get in and work with one of the parks, because they're really great places. So with that, I'll just leave it on my very cute sled dog questions slide.
Thank you very much, Alena. So questions, I guess we can either, people can, it's probably a little more organized if people put their questions on the chat. I'm assuming those are some of the sled dogs that David is now in charge of?
Yes, yeah, and they are available for adoption after 7 years of service, just so you know.
Okay, let's see, who's got some questions for Alena?
Who wants to go to Denali Park? Yeah, I would love to go back and do David's job, actually, to just work with the sled dogs all the time.
Yeah, he posted a picture of the puppies at one point, and I was ready to resign and go work there with the puppies. They were just
yeah. And well, I should also say, actually, today is the last day that you can apply to be a summer park ranger with the kennels there. So you can go on usajobs.com or .gov and apply for that position. It's a, yeah.
Okay, questions. Someone's going to have a question.
Was I too comprehensive or too not comprehensive enough? It's always that's always the question.
I have a question. Can I ask it by voice?
Yes.
All right. So great talk, by the way. Thanks. This was fun. So in the summer, there are wildfires in Alaska, and it must deposit some ash and soot on snows at higher elevation. And if it does it accelerate melting? Does it increase the, does the sun absorb, does the snow absorb more energy from the sun because of that?
Yeah, so that's 100%. That's an effect that's going on, and it really depends on the fire season. But they're getting aerosols from Asia. I mean, they're getting aerosols from super far away as well. So it's not just even the local effects, I would say. Interestingly, we've just been discussing this topic a lot in my Arctic and Alpine class, and one of the things that my students are really fascinated by is that the Greenland ice sheet, for example, there's a bit of debate going on about whether that albedo factor, the reflectivity, is more influenced by dust or actually by the algae. So there's these really crazy algae that grow on the Greenland ice sheet and help to essentially darken it. And some researchers are actually saying that it's more of an effect than the dust. And then, but funnily enough, the dust actually helps to feed the algae. So there's all kinds of little fun feedbacks that are going on. So you can expand upon and start involving microbiologists as well. But for sure in Denali, you know, there is going to be a dust effect at really high elevations. We didn't get up to such high elevations when we were doing our field work. It would be like very logistically difficult to do that. So we haven't been monitoring up there. Yeah, you could do it with satellite and remote sensing, but.
Thank you.
Oh, do dogs drink snow? I have a question. That's a great question. They do. They will bury their face in the snow to cool down, and then they will eat the snow to cool down. And they actually sleep outside. They don't sleep in the house. Some of them will come into the cabin and like to cuddle, but a lot of them will just pant all night long because they're very hot. And so they're just used to burrowing into this little, especially when they're in the field, they'll just make a little icy hollow with the sort of temperature of their body and just like snuggle up in a little self-made, little hollow space. And then when they're in the headquarters, they have little dog houses that are filled with a bit of straw, and that's how they stay warm.
And you weren't tempted to bring one home?
Yeah, definitely. Yeah, I'd like to adopt one of them in the future.
That would probably help you keep you warm in your tiny house.
Yeah, exactly. No, and the other thing that I really enjoyed doing a lot, so they obviously they pull the sleds, they're sled dogs, but they also can pull you when you are skiing. So you have these harnesses that go around your waist, and that's called ski joring. And the dogs can actually just pull you across the landscape as you're skiing, and it makes you never want to return back to normal cross-country skiing because it's really, really fast, really effective, and sort of exhilarating when you're going down slope. Yeah.
Other questions for Alena?
Everyone's ready for Thanksgiving. I don't blame you. I was pretty tired today.
I promised her that next year we'll invite her back because she is living in a tiny house that she and her family helped construct in
Really nice.
Alfred, and then she called it up to Maine, and she's been living in that tiny house. So stay tuned next year, and we'll have her back to talk about life in a tiny house.
Results, yeah. Oh, I have a question about the type of GPS equipment. So that's all built into the Magni Probe device and the computer that it comes with, but it's a little Garmin antenna that sits on a pole that feeds into the computer system. And I believe that the Magni Probe itself was developed by Matthew Sturm, who is one of the researchers I mentioned in Fairbanks, and I think he actually made that piece of equipment, and it gets used all across the Arctic for measuring snow depth. It's like the fastest, easiest way to do it. Yeah.
I'm trying to picture if you fall over when you have all that equipment strapped to you, how hard it would be to get back up again.
In the deep snow, it can be really tricky. Yeah. Some of the locations that we went to had like the snow, it really depends on the quality of snow too. If you can kind of like float on the top of a harder surface, or if you break through all the time, and that really slows you down and is, yeah, a little demoralizing.
You're probably a little bit more graceful than me when I fall over.
I learned a lot. So my boss was one of the best skiers that I've ever worked with, and she was really, really experienced with the winter camping, and it's quite a challenge, honestly, to be out at like minus 30 degrees Celsius, which is more or less the same temperature in Fahrenheit, minus 30. And to be, if you don't have a source of water, you have to melt snow. You have to really find ways to keep warm. You actually have to eat during the night just to like give your body energy. So
Wow.
It was like a pretty intensive experience. And I think if you're doing this long term, like going on a big research mission in Antarctica, it's kind of the same, but just extended. So now I know what I would be in for if I went there.
Great. Any other questions that anybody has? That was really fascinating. I really loved that. I loved hearing about that.
Great.
So thank you again, and happy Thanksgiving in advance.
Same to everyone.
And for everybody else, this was our last talk of the semester. I think we can all agree that the local talent in the Alfred area is absolutely amazing, since all of our speakers had some kind of a tie, either grew up or live in Alfred. So it just is amazing what kind of people that we have that either come out of Alfred or stay in Alfred, live in Alfred. So thank you all for coming to all the seminars, and we'll see you next fall.
Thanks for inviting me. Thanks for organizing.
Thank you. Bye. Thanks a lot, Alena. That was great. That was fantastic.
Yeah, I mean, it was really, really fun. I actually gave a version of this talk for my Arctic and Alpine class as well. So it was really a fitting topic to talk about. Yeah, enjoyed it.
Great.
It's good.
Thanks. All right.
Bye.
Bye.